Can I start now?
Let me briefly introduce you and then we can start, sir. Okay. So, yeah, once again, good afternoon, everyone, and welcome to the next talk by Dr. Sunil Singh. He's a senior principal scientist in LPL, New Delhi, and he, he's from, he did his MSc Masters in Physics from BHU. And then MTech in solid state materials from IIT Delhi, then PhD from NUS Singapore in 2008. He is expert in growth and characterization of various 2D materials, including topological insulated thin films, epitaxial group 3 nitride layers and heterostructures, and several characterization techniques like read, AFM, STM, high resolution XRD, photoluminescence, Raman spectroscopy, and for our FDP, he will be delivering or covering the topics epitaxial thin films growth, specifically using different techniques like MBE, ALD, PLD, CVD, MOVPE, etc. So, Sunil sir, I welcome and thank you for accepting our invitation and agreeing to cover these topics. Thank you so much, sir. Over to you, sir, now. Your screen is
Yeah,
not visible
so
right now.
now it is visible.
No, sir. So possibly you need to share the entire screen, maybe. Then it works better.
Visible now?
No, right now it is not visible. No. Yeah, now it is visible.
Okay. So maybe there is some internet issue because for me it's showing it is visible. So
Sir,
can I
maybe
start now?
you
Yeah.
can turn off your video. Turn off your video, maybe. Then the internet issue may not be there.
You are saying now it is okay?
Yes, sir. Now it is better. Your audio is also now clear, much clearer than earlier. Thank you. We can start now.
Yeah. Yeah. Good afternoon. I would epitaxial thin film growth technique. I will be in some other characterization technique as well. So I am from National Physical Laboratory. I think most of you know this National Physical Laboratory is the one of this National Meteorological Institute of India, and we have to also do this 7 SI based units. Research on the quantum gauge, other things in the process. So just I will give brief introduction about the nanostructure and especially thin film growth, and then epitaxial thin film growth. Why? What is the role of substrates? And then I will discuss this epitaxial thin film growth techniques like MBE, ALD, and PLD, and some of the characterization techniques like read, HRXRD, STM. And then I will go one by one overview and examples of various epitaxial growth techniques. So when we just start with the nanostructures basic, because I think some students also joining online. So we know this nanostructures is well known from the last almost 20 years. That the word nano means that we have the billionth part of a unit in general. And when we are talking about the thin film or something like, so we are talking about this nanometer that is in length dimension. And it's
Sunil sir, somehow,
depends on the 2D.
Sunil sir,
Yeah, yeah.
sorry sir, sorry for interrupting, but your audio is intermittently breaking actually. I'm not sure how to handle this situation. It is from your side. Participants are also mentioning that some audio is breaking. Sunil sir, can you hear me? Right now, there is blank screen. We see that we are viewing your screen, some shared screen, but no content is there. And also we cannot hear you. Yeah, dear participants, there seem some network issues from the speaker side. He is reconnecting from different device.
Yeah, hello.
Yes, sir. Now your audio is really very clear,
Okay,
and we can see your screen.
okay. So now, yeah, so now, sorry, I just connected with my laptop. So, okay. So I will try to finish quickly. Yeah.
Sure, sir.
Yeah. So anyway, so basic we know these nanostructures. Now I am moving towards this why these nanostructures make it unique and interesting. So I think already this talk is going from the last almost 1 month. This quantum size effect. So that is one of the parameter, that is quantum confinement effect. So this is the basis for this having this quantum materials as well. So of course it depends on the what is this dimensionality of the materials, like whether it is three-dimensional or two-dimensional quantum or well or quantum wires or quantum dot, depends on the what is the dimensionality. And then the history of states function we can see clearly is changing when we have the changing in the system of the different dimensionality. So when we are going to fabricate these devices or even futuristic devices on basis of quantum materials for the quantum computing others, of course, always happening there is two different approaches to have the fabrication of the devices. That is, one is the top-down approach. It means we can use this some nanolithography or lithography, etching, and EBL system for the nano devices. So, for example, this is the one of the technology like 14 5 nanometer technology from the Intel, that is made by using the lithography and etching process. Another approach is the bottom-up approach, that is the manipulation with this STM, even the self-assembly process. So this is the famous statement from the Professor Richard Feynman in 1959 lecture. There is plenty of room at the bottom. So what is the meaning of that one? So of course we can when we can start the making the devices or making the materials or making the thin films using these atoms or molecules, then of course we have the more control. And this is the one other example, like even people have make this 48 iron atoms on the copper surfaces to make this quantum coral. And that is, even you can see this uh, um, this quantum waves are means standing wave inside even in the materials. This is the another story, but today I am going to focus why we are interested in the, especially in the epitaxial thin film growth of the self nanostructures. So of course when we are talking about this self assemble means it can be formed the growth environment taking advantage of some energetic, kinetic, and geometric effects. So of course, there is no need of lithography, very low cost and parallel process. But again, the remaining problem is, of course, we are going to solve one by one. This precise control of the size, shape, type, and location of nanostructures. And more important is understanding of the growth mechanism. Means we can know how we can control the morphology, or how we are going to make this single layer or multiple layer. It depends on the if we know the what is the kinetics, surfaces, thermodynamics, and mechanics. So when come to the real thin film growth mechanism, this is the three uh, basic thin film growth mechanism. One is called this Frank von Wandermeer mode, that is even we call layer by layer growth. In this case, what happens when the surface energy means substrate surface free energy is more than the interface and the film, then your film will be growing by layer structure. This is the one about the example, like we have grown this gallium nitride and gallium nitride, and you can see this is the layered structure has been grown. Another different approach is when the surface energy of your substrate is less than interface and this film, then it means you are growing this island growth. So this is the one of the example. For example, when we are growing this antimony and graphite, you are getting only the island structure. There is no film structure. In between, there is mechanism that is called the Stransky Krasnov mode, and even that is also called this layer by layer followed by the island growth mode. So here what happens first, it have the small interface energy, and then strain energy happens due to the lattice mismatch of the different substrate. For example, we have used silicon and germanium. Then here we can see this first some silicon will make germanium will make some layer, and then after that it start to making the germanium quantum dots. So this is the like layer by layer, few layers, and then after that it start with this island mode. So now, as my topic is to discuss about the different epitaxy growth systems. So first, just I would like to know, means at least I have to give some idea of why what we mean by epitaxy growth. So generally, when we grow the film on the substrates, then it depends on the what is the growth temperature, growth rate, and what is the substrate and what is the growth techniques, and then accordingly we get mostly 3 to 4 different kind of the crystalline or structures when we are talking about this. So one is the amorphous structure, like people even use amorphous silicon for the silicon solar cell application, but most of the devices, of course, we are not interested to grow the amorphous structures, because these amorphous solids or liquid have the no long range order. It means the quality we don't know, means certainly the morphology will be different, and there is no any periodicity or even no local periodicity, then it is very hard to know what we are growing. Another is the polycrystalline film. So basically, this polycrystalline film refer to this. We have this different thin film composed of numerous small crystallites or grains, where the film structure can vary in phase content, nanoparticle size, and thickness, and influenced by the synthesis conditions. And third is the single crystalline. So this single crystalline means we can grow the very single crystalline structure, like before my talk you have already uh, this have listened the talk by Professor Surjit Singh, that he already growing the single crystalline single crystals. So it means we have the single crystal have the infinite periodicity, and then of course we have this bulk materials with the continuous unbroken crystal lattice. So using this kind of single crystalline, for example, silicon, gallium nitride, gallium arsenide, whatever, there is the process that is called the epitaxy. So epitaxy is the process of growing the thin film of this kind of single crystalline substrates, in which the substrate determine the crystallinity and orientation of the growth layer. So why you are interested to grow this epitaxial thin film growth? Because already if you grow the single crystal, you have the you can do a lot of the things. But the problem, like when we are talking about the numerous devices, then this epitaxy process, because we are growing the film on the top of the single crystalline, then we have the option to have this precise doping, control thickness, and the creation of the heterostructure. Because it is not necessary that only 1 or 2 layer is important. Maybe we need maybe 10 to 20 different multi-layer structures, or one layer by layer structure. Then in that case, this epitaxy will play the importance role. So that's again, of course, we have to see what kind of the technique we can use for the epitaxial growth, and some of the characterization techniques. So again, epitaxial growth is have the two different mode, that is the homoepitaxy and then heteroepitaxy. So homoepitaxy is the same, Like when we have this like thin crystal layer, lattice is the same as that of the substrate. For example, if you are growing silicon film on the silicon substrate or gallium nitride and gallium nitride, then we can see it is the homoepitaxial film. When in the case of heteroepitaxy, when we are growing the thin crystal layer of the different form, that of the substrate. For example, if you are growing the gallium nitride on silicon or gallium arsenide on silicon or germanium on silicon, then this is the heteroepitaxy. So again, when we are talking about the surface morphology in homoepitaxy, it is not necessary that when we are growing, similar layer like silicon on silicon, then it will be very smooth layer or very, means layered structure. It depends. Of course, in ideal situation, you can imagine this is the layered by layer structure, a step flow growth mode. But it depends on the what is the growth temperature, what is the deposition rate, and then accordingly you have to find out what is the equilibrium growth condition. Then accordingly you can find out whether we have this layered structures and still there is some kind of the uh, nano structures or even some defects. So, like for example, at low temperature, high flux, you can get like some kind of the nucleation start. But again, you have the layered structure. But here again, you have this kind of the pits or defects on the epitaxial layer. So it means this is the if you have the temperature and growth flux, then their transition should be not like transient. It should be like very smooth, means whether it is temperature and flux is will be optimized, then accordingly you can control the roughening of the substrate. So of course that's one of the requirement when you are going for the precise doping or precise making the smooth homoepitaxial layer. So as I mentioned, of course, this lattice mismatch is the one of the parameter that is people are always worried about this one. This is just one example I just saw uh, why we are interested or why we are so much interested in the lattice parameter with the different materials. So one of the example I have taken, that is a third nitride semiconductor. So here we can clearly see this x-axis of the lattice constant, so it is varying from 3.1 to 3.5 angstrom. But when we are seeing this band gap, it is changing from 6.2 to 0.7 electron volt. It means when we are making such kind of the nano structure epitaxial thin film of third nitride layers like in indium nitride and aluminum nitride or gallium nitride or aluminum nitride, then there will be low lattice mismatch. But you can change the huge property, like even if you are doping this indium or aluminum, we can see we can cover this band gap from the starting from 0.7 to 6.2 for the different purposes. So that is the one of the beauty of the making this different nanostructures, means especially epitaxial thin film growth, having the low lattice mismatch substrates. So when we are coming toward this, how many techniques we have? I have just written few of them. Then this basically this is the one of the well known. This is the molecular beam epitaxy because already epitaxy term is here. Then chemical vapor deposition also we can use pulse laser deposition. This is the laser MBE. This is the new terms that is combined of the PLD and MBE. Also, atomic layer deposition can be used for the making this epitaxial thin film. Then this MOVPE, actually MOVPE, metal organic vapor phase epitaxy, and metal organic chemical vapor deposition. Actually both are the almost same. Only this, they change the name. And then of course you have the hydride vapor phase epitaxy. And it is not necessary that always you have this epitaxial film. Even if you have the more control or if you have the more high vacuum, ultra high vacuum system, or even good quality of the even sputtering system or even EV operator, still you can make this some kind of epitaxial. At least not at least you can make the single crystalline or single oriented film. So it is not necessary that always MBE and PLD required, but it depends what is the application. When we have the very uh, small size, then even you can use this some kind of the this e-beam and other technique. But for the larger, we of course we have to use our more control. Then MBE and MOVP or MOCVD is the more preferred over the other techniques. So as I mentioned, UHV system. So this is the system that is we called means ultra high vacuum. So just to basic, I just wanted to highlight why we need this ultra high vacuum system. Why we are not able to do this epitaxial thin film growth or thin film growth in the normal environment, like using this some chemical route. Of course, you can do, but the purity and when you are talking about the control over the precise thickness and then impurity free film, then it means you need some vacuum. So we started with the basic vacuum, like we have this 1 atmospheric pressure to 10 minus 3 millibar. Then the high vacuum, we can say, consider 10 minus 4 to 10 minus 6 millibar. Then ultra high vacuum, it is 10 minus 7 to 10 minus 11 bar. So why we need UHV system? There is two reason. One, we have this, you people have this heard about the mean free path. So when we have this vacuum region from 10 to minus 3, then this your mean free path is around 5.9. So it means around 5.9 centimeter. But when you are having this more, like minus 8 minus 12, then you have the in the vacuum free mean free path is are almost in the range of kilometer, or at least more than, yeah, 100 meter to 1 kilometer. So it means when you are growing some of the elements or some beams is in the inside the UHV chamber, so it is going to directly hit your substrate. It is not going to collision with other things or making anything. So that's reason it is mostly coming as a form of the beam. And another approach is like when you having the very clean surface, then people say that it is one monolayer thick. Even film can be grown, means even from the inside the chamber in the 1 second if the vacuum is into the minus 6 millibar. So it means if you have this ultra high vacuum system, once you put the substrate, still you have some few hours to process, and then there is no there is no other growth on the your substrate. So that's the reason your interface will be made very mature, means very high quality, and there will be no any other contamination on your growing substrates. So just I try to highlight why we need the UHV system basically when we are talking about the MBE and other growth process. So come to this molecular beam epitaxy. So molecular beam epitaxy, you can just see basically what happens when you are growing the thin film. So basically we have this atoms or molecules are coming from your effusion cells, and then this is your substrate. Just to know what, and then on the substrate a lot of things happening, whether like atom depositing on the substrates, then it is collision to each other, or they are making the clusters, and even after that making the layer, or even if you have the very high temperature, even some of the atoms evaporate from the surface. So it means when you are growing the film, it is not necessary that you should be growing always the good quality of the film, but first you have to optimize your what is the growth temperature, what should be the deposition flux or growth rate, and then and then of course cleaning of the substrates, and then selecting the different substrate, like we having this low lattice mismatch with this growing film, you are able to make this epitaxial thin film growth. So so always it happens like how we are growing means even why MBA is so important. So one is of course we use the different beams, like we have these different diffusion cells, and another thing is MBA have this most of the MBA they have equipped with this reed, that is this called the reflection high energy electron diffraction technique. So even inside the growth or during the growth process you are able to see, or at least you can know where is your substrate is clean or not, single crystalline or not, and then if you are growing the film, whether it is single crystalline or polycrystalline amorphous, or even you can know whether it is a smooth film or whether it is the rough or 3D growth of the film. I will just show some of the how this read is having important. So read generally we say it is the in situ monitoring. In situ means when we are growing the film, we are able to see the what is the crystalline structure. So what reed can do, just to sensitize that this can, even we can use this substrate thermal cleaning monitoring, because we also need to clean the our substrate, not only outside like using acetone, HF and all other thing, but also inside the chamber. We want to heat by the thermal cleaning, basically like heating up to 1000 or 850 degree. For example, to remove silicon oxide from silicon, we have to heat 850 degree, because even if you, whatever you are cleaning, if you are loading inside the chamber, 2 to 3 nanometer silicon oxide will be there. So for the removing that silicon oxide, we have to clean inside the vacuum, so that is like 850 degree in the UHV, and then we are able to see clear or very, means silicon oxide free silicon. Then again, you can monitor using the read. Then this controlling initial growth stages, we can see whether it is growing or not, making the different phases or not. Then of course, even we can have this monitoring the surface structures, and then growth rate measurement as well. So so basically, how it works? Basically, we use this different accelerated electron beam in the range of 5 to 30 keV, or even some of the system, of course, they have this 100 keV system, and then this have the very low glancing angle. It's less than 3 degrees. So it means we are able to see only on the surface. I will just show in the next slide. So this is the one of the sample holder, and you have the sample, and then this is your electron gun. This read gun is coming, so your theta value is very low, around less than 3 degree. It means whatever the information you are getting only from the surface of the top surface of the your substrate, and then you have this detector or CCD, and from here you are measuring. So this is the one of the read pattern, how it means. For example, if you have the single crystal structures, your beam is coming then reflecting back, and from here Evaldi sphere, you know this Evaldi sphere, this inverts are this form of the Bravais lattice, and from here, if it is single crystal, you can see you are getting this three lines structure. It means it is showing the this have the sticky read pattern. Same thing, even you have the single crystalline, but they have the island type of structure. Then this beam is coming like this and then reflecting back. That's region from the Uvalde sphere. You are getting this spot. That is, we say this spotty, and then spotty it is showing this your surface is very not smooth as compared to the first one. And another is this polycrystalline. Then in the case of polycrystalline, you are able to see only this kind of the pattern. So it means there is no spotty, no sticky, but it is showing the all the way formation. It means showing the you have the polycrystalline structures. And how this read growth monitoring happening? Read growth monitoring, you can clearly see like once this there is no growth, you can clearly see beam is going back. Then after that, once you have the more, then it means already this beam has a deflection. Then accordingly, you are able to see the how it has been growing. And then even during the intensity acceleration, even you are able to see the mode of the layer growth, whether it is growing with the 3D growth or 2D growth. I will show some of the real example of the read. So as I mentioned, this molecular beam epitaxy is an epitaxial growth technique used to deposit thin films of the single crystals. And this is the some of the like K cells. That is also we say the effusion cells. Then you have the substrate. Substrate you can heat up to 1000 degree, depends on the what is the uh, purpose to growing this epitaxial film. But mostly we have the this heating up, means we can heat the substrate up to 1000 degree, because we want to know do this substrate cleaning by the thermal heating. So like removing the silicon oxide from silicon, at least we want 850 to 900, and for other purposes. And then you have the read, and then from here you can monitor the how the growth process happening. This is just another view of the picture. So we clearly, I just here you can clearly see like substrate, and then one of the more mostly this kind of the techniques MB, they have the rotation also. So it means during the growth, your substrate will be always rotating. So it means you have the more uniformity, because if it is the only and there is no rotation, then it means there is some chances that maybe the one place it is more growth and other place maybe less growth. But once you have the rotation, then it means you have the uniform growth. So I just mentioning that this effusion cell, when we are talking, then this basically it helps to generate the molecular beams. So this process happening, like if you have this high purity solid materials like gallium, arsenic, heated until they begin to evaporate. Means it depends on the what is the vapor pressure of the that materials. Accordingly, we have to heat this materials, and then inside the cell, this material reaches at a specific vapor pressure, and then because the cell has a small opening leading into vacuum, the atoms effuse out. And as I mentioned already, we are doing the process in the ultra high vacuum system. It means there is no other scattering and anything happening to your beam, and then it is going directly to the substrates. That is, we call this ballistic transport. And then of course the surface kinetic process is happening, like when the atom strike the substrate, the atoms bonds extending the existing crystal lattice seamlessly. It depends on the what is the growth temperature, what is the flux. Accordingly it makes whether it is 2D or 3D growth. And then you have this shadow masking, means you have the shutter principle. So basically each effusion cell have the shutter cell. So if you want to grow one, then another material, then you can quickly close one shutter and then open another shutter, then you can make the different texture. So that is the having the advantage of making the different heterostructure. It is not necessary always you grow one film. For example, gallium nitride on silicon, but even you can make silicon, then gallium nitride, then if you want, then you can make the indium nitride, and then different layers. So that's reason we generally have this MBE 4 to 5 fusion cells with the different materials, and then accordingly you can make the heterostructures. So when we are talking about the advantages, of course, it have the various advantage. Even you can grow, very uniformity, even precise control over film thickness. Even one monolayer you can grow. Means that precise you can use the MB. But of course, if you see the limitation depends on the. This is very slow deposition process, and most of the things is this equipment is very complex and expensive. So of course it depends whether we what is our application. If you are going for this solars and another, of course then we are not worry about this MB. But when you are going for this quantum devices or quantum anomalous Hall effect or some other purpose where really this kind of the epitaxial required, then definitely we have to go for the MBE system. So this is the one of the example. Even people use this CuInSC2, means even not only two, even ternary film they are able to grow using the MBE system. Then this is one of the example like CDT thin films grown by MBE. And this is the gallium nitride structure, because we have the gallium nitride growth system, means MBE and laser MBE at NPL. So this is we have already done most of the experiment in the past. So we can clearly see, this is the read pattern. So from the read pattern, even some literature like this is the nitrogen rich, which means showing the read pattern is spotty. And then accordingly, we are getting the rough surface. In case of the streaky reed pan, we can clearly see the formation of the layered structure of flat structure. That is the 2D growth. So we have also grown this some gallium nitride and gallium nitride. That is example of homoepitaxial. So before that, we have this very high quality this 2D this gallium nitride on sapphire substrate. And then after that, we have grown with the plasma enhanced MBE system, that is at 730 degree. We can clearly see, we are able to see this terraces are increasing, but the pits are some kind of the hexagonal and small pits are going. So that's reason we again change, all the parameter remain same. We change the temperature 730 to 740 degree, and here we are able to see these defects are minimizing, especially this larger one. And then in case of 750, we can clearly see we are getting the very high quality and larger terrace. So that's reason we are able to make some kind of devices on the large because we want a large smooth area. And of course, there is another approach that we can have these different dopings. Then we can make PN and other kind of the devices, or even for the LED and other applications. So another system I will just discuss this pulse laser deposition. So this pulse laser deposition is again this is the physical vapor deposition technique in which this high energy laser is focused on a target materials. So this is, for example, you have this target, and this is your substrate, and then here you have the laser. So laser is falling on this target and then hitting, and then this laser plume is coming out, and then on the substrate here you are growing the film. So if you see MBE and PLD, of course, there is one difference. Of course, if we are saying the PLD, it means we are working in the high vacuum system. It is not required ultra high vacuum system. But I will show also some of the example when we have this PLD in the ultra high vacuum system. So here, instead of every system like in the MBE, we are not using the KSL, but you are using this laser, this means target material. Then accordingly you have the laser, and then you are having the substrate. So these have the advantage PLD, because already you have been making this energetic particles coming from the laser. So it means you have this high energy kinetic particles, and then going to the substrate. It means you are going to reduce the growth temperature of the film. So that is the one of the advantage to having the PLD. So of course, when we are going to what is the working principle, we can see this first this pulse laser deposition we can divide it into 4 steps. So in first step, this absorption of the laser on the target surface and interaction with the materials, ablating and plasma formulation. Second is the plasma dynamics and laser plume interaction. Then third is the depositing of material separated from the target on the substrate. And fourth, as usual, whatever the process in the MBE, this nucleation and growth of the thin film of the materials on the substrate surface. So again here there is some physics of laser ablation, because when we have this laser is falling, means in the generally we have this nanosecond pulse laser, then in the surface absorption material excitation, then after that it is the thermal evaporation, then after that this plasma absorption and self regulatory regimes, and then accordingly you are going in the millisecond, then you have the plume. So this is the one of the process. This is the not, but of course we are pulse. We are giving in the nanosecond region. That's reason we are not. There is no delay, and that's reason we are getting the continuous field. So already I mentioned this one. I just ignored this one. This is the same procedure like when we have the deposition on the substrate. Again, this is cluster nucleation, then diffusion to clusters, then making a different cluster, and finally that is making the thin film on the surface. Okay, so generally we are talking about the which laser is commonly used in the PLD. It depends on the what is the application. So most of the PLD works are, even we have seen, they use the uh, different UV length PLD sources. That is like uh, this is the 308 XECL, and then 248. This is the KRF laser, ARF region 193, 157 nanometer. But also some of the people use this NDAG laser. So that is the one of the principle, means we have to select. So basically, when we have these eximers lasers, then have this for the advantage of high power output and stability. In case of NDAG, it is the simple and it is very easy to maintaining compared to this NDAG, this excimer laser. So it depends what is our budget and what is our application. Accordingly, we can select the laser. So as I mentioned, advantage is having this when we have this control over the growth temperature, and then we can have this even you can use this uh, materials that can't be grow at high temperature in MB and MOCVD. You can use this PLD for the low temperature growth. So this is one of the example, like you even you can make this two like COFE thin films. You have the target of COFE. You can control, means make the target of the different material, like 20% cobalt and 80% iron, and then of course you can make the divisor. And here we are able to see clearly formation of COFE. One of the example, like this also equipped with the reed. Even you can make this JDNO thin films using the this PLD. So as I mentioned, yeah, sorry. So now it times comes, even we can combine PLD and MBE growth techniques together. That is like already I mentioned, this is the PLD, this is the MBE system. But what happens when we have this all the systems like similar to the MBE, but instead of a fusion cell, we can change only with the PLD targets. Then we can make this, we call the laser ME process. This is the system that already we have at the our national physical laboratory, and this is the our real system, means schematic. So of course we have the load lock chamber. Okay, so I forget to mention that in the MBE system or any this kind of a system, basically we have the two, at least minimum two chambers. So one chamber is called the load lock chamber. Another chamber is called the main chamber or growth chamber. And here we have the gate valves. So it means when we are putting the substrates, first we transfer from the vacuum, atmospheric to the load lock chamber. Then we starting the load, and then this is already gate valve is closed. So this chamber mostly always 24 by 7, it have the ultra high vacuum system, 10 power minus 10 millibar vacuum inside. So once we have this all the process, like even we can heat up to some degree, like 100 to 200 degrees Celsius of the substrate. And also this chamber also have this roughing and turbomolecular pump, so at least it will reach to the minus 5 to minus 6 range. And then from here, after that, we can open the gate valve, and then we can transfer the sample from here to here main chamber. And then after transferring, because it's a quick process, maybe within 2 minutes you transfer the sample, take out your this transfer arm, then close the gate valve. Then within 10-20 minutes again your pressure will be as good as like 2 to minus 10 millibar. So we have to maintain the pressure in the of the main growth chamber always in the UHB region. So this is the one of the system, like we always have this MBE or even laser MBE system. We have these two chambers. So as I mentioned, instead of the fusion cells, here we can use our PLD targets, and this is the lasers. So this is the only difference. Otherwise, we have the read. We can monitor in situ. We have the residual gas analyzer. We can have this whether our chamber is clean or not. Even any issue, then we can detect. Yeah. And then also we can substrate. We can heat up to 1000 degree. We are able to rotate the substrate. Then plasma also can generate. So this is the one of the example, like when we are hitting this laser, this plume is looks like the blue plume. So this is the a real image at the CSIR and PL. So here we have this. This is the main chamber, as I'm mentioning, and this is the back side, and this is our transfer arm. So from here we are transferring in the main chamber. This is the read gun, and here all the system is controlled by this computer, and we have the vacuum to 110 millibar. And then accordingly we are doing all the process. Even we have this different target. We have this liquid gallium target, then also this solid HBP grown gallium nitride target, and depends what is the application. Then accordingly we are selecting the targets to make the, whether we want the smooth film or nanostructures. Then we are having the different targets. So So here I wanted to show how we are going to see, means all the process, how what is the cleanness is more important. So this is we have cleaned using the this sapphire substrate after the chemical before loading in the load lag chamber. We can clearly see still some kind of the small particles or small dust particles are there. After that, we put inside the UHV system, as I mentioned, from the load lag chamber to the bench chamber. We heated up to 850 degrees Celsius. Then we take out and then we do it the AFM. You can clearly see we are not able to see any dust particles. So it means already surface is very clean. Even after that, we have done this, for example, surface nitridation. It means because aluminum oxide, then we have this nitrogen on the top. It means it is making this aluminum nitride OX. Then here we are getting almost smooth surface, like surface's roughness is decreasing. And from here, after that, we are growing at different materials like what is the application at what temperature. And we can clearly see the formation of the high quality gallium nitride film. So this is the one of the advantages to having this uh, high growth, means high the substrate heating at the high temperature to clean the substrate inside the UHV system before making any growth procedure. So we can see like when we started with the different temperature like 600 degrees Celsius, we can see small grain size. Then we grow the high temperature 700 and 720. We are able to see this crystallite size increasing. So that is the one of the parameters to control. Means not only the growth rate, but also you have to see which temperature have the more. And then when we are even hitting 750, again we are getting very irregular surface. It means this 750 is too high and then 600 is too low, so we have to play between 700 to 720 degrees because we are getting the very large crystallite size compared to the 600 and 750 degrees Celsius. So already I saw this read. Then this one of the parameter that is we can do mostly XC2 to know whether our crystalline structure is good or not. That is the HRXRD. So HRXRD, again we have the different modes. That is the one in the 2 theta scan to determine the crystalline structures, whether it is amorphous or polycrystalline or single crystals. Then another is the phi scan. So this determines the degree of in-plane alignment of the film relative to the substrate. And third is a more powerful technique is racking curves. So this is the racking curves. You can from the racking curve, that is we say the X-ray racking curve, and from this FWHM value, we are able to see which kind of dislocation density. And again, it depends on the what is the material. For example, for the gallium nitride, this is the equation for the screw and edge dislocation density. So this is the one of the powerful techniques for the uh, knowing the crystalline structures or crystalline morphology. This is the one of the example. For example, we have done this. This is our 2 theta omega scan. Means this is XRC racking curve. Looks like this, and then we have the different temperature. And from here, we are able to see that when temperature is 700, as then we are able to see the very low FWHM. Means it is showing the very high quality of the formation of the film. So as I mentioned previously, from the read, like already equipped with this in the MBE or even in the laser MBE, we are able to see whether our film is growing in the what mode or our substrate is clean or not. So this is, for example, we have this flat gallium nitride template, and then we clean inside the chamber. Then we can see the sticky read pattern. So it means showing the 2D flat film. And when we are having this growth of the gallium nitride using laser MB, because we intensely want to make some kind of a nanostructures, epitaxial GAN nanostructures. So for here we are able to see this spotty read patterns. And once we do the surface morphology, we can clearly see like we are getting some kind of the nano wall structure. So this is the one of the technique. Even before growth we have the expected that we are going some kind of the 3D structures or even more nanostructures. So that is we can judge by using this read technique. So people say why what is the advantage having nanostructure? This is the one of the example when we are growing this gallium nitride nanowall and gallium nitride template. We can clearly see like this is the gallium nitride photoluminescence peak, and this is from the nanowall. So there is shift up around 90 MeV, this near band edge emission compared to the bulk gallium nitride, and it is mostly coming from the quantum size effect, because once we have this tip width of the nanowall, it is coming around 10 to 15 nanometer, and which is compared to the Bohr excitation radius of gallium nitride, that is 11 nanometer. So this is the one of the example. Even we can see this quantum confinement and quantum size effect even on the gallium nitride nanowalls grown using this laser MBE. So again, we have done this different nanostructures. It is not necessary that only we can grow gallium nitride on sapphire and only nitridation, but even we can use this buffer layer also. So for example, here we have grown, first we have the sapphire, then after that we have this nitridation, then after this we have this aluminum nitride buffer layer. Then we have grown the gallium nitride. So it depends what is the application, and then accordingly we can go for the different nanostructures. So we have done some kind of a device management. I will just skip this one just to show, and then we have grown some different nanostructures uh, on the different substrates. I skip this one, and then I just go in the last. So here we can clearly see that from the read pattern, here we are able to see whether it is having the high quality or not. So in 500 600 the read have showing the very good quality, and from accordingly this XRD is also complementing to the read pattern. Same thing like when we have this uh, gallium nitride reach condition, then here we are able to see the this spotty pattern. But once we have this very smooth gallium nitride growth at 400 degrees Celsius, we are able to see the sticky read pattern. So this is the AFM and plus read. So from here, even we are able to see the control growth of the gallium nitride film at low temperature in the laser MB system, and the read even before doing the FM, we are in the process, or we know this is that mostly we are going to get this smooth film. So this is the first part. I finish. Can I take a 2 minute break? Then we can start another part.
Yes, sir, sure. We can take a 5-minute break here and then we start again for
Yeah.
the
Okay.
second row. Yeah.
Yeah. Okay. Thank you. Yes. Can we start now?
Yes, sir. Yes, sir. We can start. It was really nice background photo on your desktop. We can see. uh, so
Okay, if you allow, can I show some of the video because to have the audience or at least to the faculty members, they can have the feeling how PLD laser MB works. So can I share some of the video for 2 3 minutes?
no
Then
problem, sir. This will be really nice.
yeah,
Thank you so much for considering this. We can see the video, and it is true that the video will demonstrate. Actually, it feels like seeing live growth.
yeah. So are you able to see the video now?
Yes, yes, yes. We can see the
Okay.
screen.
And basically, we have a lot of systems. So first, I will describe this laser MB system that is basically made for this third nitride film, like gallium nitride, indium nitride, indium nitride. Then you can make this thermally alive. This system has this USB system, and then it can right now it can go to the 10 millimark. So here we have the read facility. So from read we can have this in situ growth, like you can monitor, like camera is fitted, and this camera is going to connect with the computer. So from here you can know what is the planning. So this is our we can put the substrate rotations from can rotate the substrate. This is our substrate filter, and then we can keep putting this power supply to up to 1000 degrees. So, so of course, this chamber we need a very high load temperature like 700 to 800 degrees Celsius. So we don't want to clean up this chamber. So for that one, we have all this liquid nitrogen. From liquid nitrogen spectra, we can flow the nitrogen from here. Then it will be putting our chamber. This is to minimize any kind of contamination. So as we know, for gallium nitride, we have the gallium nitride target. Then we have the nitrogen plasma. So this is our nitrogen plasma cell. From here, we can have this RF nitrogen plasma cell generated. And for this sputtering, of course, we for the first delivery portion, we want the laser. This is the entry point for the laser. So we have this laser, laser. From there, that system, and also this for this one. Then this light laser here, and then laser will go from here. Then it will go to the. So this is the one of the arrangement that even one laser can be, because this laser has very expensive process. Like when we have this laser, you can see how many cylinders we have. We have 1, 2, 3, 4, 5, 6, 7 cylinders. So out of this, of course, we have nitrogen. Then this the mixture of chromium and chlorine. So that is our KRF laser. So of course, we can see other lab, other facility as well. So I will go other. Can go nitride field. Then also we are able to go to oxide field for the oxide field. This system also has this pumping system, and then we have this. To get this information about this student, especially working on this student. So here we can see that all the this form we have this turbo molecular form. Then we have this mark to controller, then heater are already like heating to 830 degrees Celsius for the cleaning and other process. Then again, this laser will come directly from it. Same laser we can take the other. And we have the two lasers. One, we have 4 PLD chambers for the different purpose, like some for this side material, this for this cooling material both. And once we get the bill on the device, either we use this thermal electric. This all the one of the tab and all the both related to possible and other I think we'll show in some other video how it works. So
first of all, to make it on, we have to switch on the main power button, and then we have to switch on this one, the main, and then this key. We have to put this from 0 to 1. Okay, it means that the laser is started. So we will talk about mainly the KRF laser. Its wavelength is 248 nanometer. So we have already built the KRF laser, but it is a poisonous gas. So we have to use the exhaust, which is going from here to outside, so that we cannot get contaminated or something. So the second thing we have to keep in our mind is that we have to use chiller if we are using the laser on above the frequency of 10 hertz. But if we are using it below the frequency of 10 hertz, then there is no need of the chiller. So to make it on, we will run this power button, then enter, then execute. So we will wait for the laser to be on. After the laser is on, we can hear the sound of tick, tick, tick. As we can see on the display, the frequency is 10 hertz and the voltage we are using is 22 kilovolt. And it is the energy that is showing. But we on the window, we have to measure the energy. That what is the energy that we are getting on the window. KRF examiner with wavelength of 248 nanometers in range. And the energy is tunable per pulse. And the frequency also we can vary from per hertz. The energy of this laser also range. So while deposition, we should take care of our eyes by wearing this goggles. The laser used to come through this exit port, through this attenuator, from which we can vary the energy of laser, and it falls through this deflection lens, through which we can focus laser onto one particular chamber. And this is the laser control box, from which we can vary or change the parameters of laser. The laser beam is focused through this chamber, and from this laser focusing lens. This is our deposition chamber, which is connected to the vacuum pump through this line. And we can create vacuum while deposition up to the order of 10 to the power -6 millibar. This is our target stage, which is connected to motors, and we can rotate the target during deposition. These are the vacuum gauges, from which we use to monitor the vacuum inside the chamber. This is our target carousel, on which we can place 6 targets, and we can deposit multi-layer also by ablating one by one target. Coming to our substrate heater, this is our shutter of the heater, which we used to remove while deposition, and this is our substrate, which I have pasted on the heater, and we can heat the substrate also till 800 degrees Celsius. Now I'm going to load this substrate inside the chamber. Now we need to create vacuum inside the chamber. So I will open the valve with the pump is connected. Right now I'm opening the valve. Now we have achieved the high vacuum. And since we use to deposit excitement in this particular chamber, so we need to allow this gas, which is oxygen there. And the partial pressure with oxygen is 5 10 to the minus 2 millibar. Now I'm going to turn on the laser. Here we can see that after striking laser beam onto the target, the plume formation is there. The plasma consists of the ablated material which used to get deposited onto the substrate kept normal to the target. And the current laser parameters we have used is energy density to 1 joule per centimeter square with the frequency of 1 hertz. We can control the deposition time according to the desired thickness of the material. And now we are moving on to the few of the deposited films. Here we have deposited 2 films. Depending upon the 2 different materials, we have used 2 different substrates. This one is barium titanate on silicon substrate, and the next one is lanthanum titanate on glass substrate.
So I will also just show how this read pattern we can clearly see from the read. So this is the during the read we can see this is the movement of the read means rotating the substrate, and from here we are able to see cleaning of the sapphire is going on. So similar thing like you can clearly see when we have this uh, buffer layer growing, we are clearly see the same thing. Now we are able to see this read pattern is spotty read pattern. So this is the one of the read facility in situ read monitoring. We can see whether we are growing the cleaning substrate. Then after that we can grow the film, and then from here we are sure that we are getting the highly crystalline or single crystalline film. So this is the, for example, last minute growth. We can clearly see very bright this read pattern like spotty read pattern. So from here we are able to see how the growth is means making the 3D, and then of course we do the AFM, XRD, Raman, PL, etc. after that. Okay, so now I am moving to the second part. This is just So my slides are busy now. Sorry, visible.
Yes, sir. Slides are visible.
Okay. So as already time running, so I will just try to have some kind of the basic of the ALD and MOVPE and CVD system. So already we discussed some of the process in the previous talk, like AL, PLD, laser MB and MBE. So I will skip this one. Okay. So one of the technique that is, we say this is atomic layer deposition, that is ALD system. This is again this one of the physical vapor deposition techniques, but here we use the mostly the chemical precursors are sequentially introduced to the surface of the substrate, where they chemically react directly with the surface to form the some monolayer. So atomic layer deposition, because already from the name we can see this, we have this control over very 1 to 2 nanometer. And of course, as I mentioned, different techniques have the different advantages. So of course, from the ALD you can grow again this third nitride and other materials, but mostly ALD used for the oxide materials like aluminum oxide, titanium oxide, hafnium oxide, zirconium oxide, because these are the oxides, when you are making these MOSFET devices, then these high K dielectric materials like these oxides can act as a, making the this gate dielectrics. So that is the one of the reason that ALD playing the important role. So again, this ALD have this like sequential process. We can use one or two or three precursor, depends. For example, when we have this first precursor, then we make the dose, then we purge. Then after that, we put the second precursor. And then after that, it started to evacuation. Then we have the heating. So accordingly, unlike chemical deposition, ALD precursor are not pumped simultaneously, but they are pulsed sequentially. So it means you have the different precursor. It depends on the what kind of the oxides you want, like HFO2 you want or aluminum oxide. Then accordingly you have to select the materials, and then you have to go for the growth of the this kind of the materials using the ALD. So, of course, this is the process like precursor A in plug, then purge, then after that precursor B, and then purge. So you have to follow the process, and then after that, uh, when you want to like thickness like 1 to 2 nanometer, 10 nanometer, what is the application? Then accordingly, you have the procedure to know what means which one sequence, how much thickness you can grow using the atomic layer deposition system. So of course, advantage, as I mentioned, first advantage of having this atomic layer deposition is that is the control of the film thickness. Even you can control the film thickness up to 1 to 2 nanometer. Then excellent repeatability, and moreover, it requires very low temperature processing compared to the other CVD process. So of course, a limitation is this time required for the chemical reaction. Then also you have to know what is the recipe, and then what is the material you are going to use. Then accordingly you have to see how much cycle or how much process you have to follow. So again, this there is a lot of different ALD process. That is, one is thermal ALD process. So here you use this normal heating up to 150 to 350 degrees Celsius, and here we can use this variety of material can be deposited. Like I mentioned, mostly this is used for this oxide materials. Of course, people started with some other nitride metals, but this is not too much required. Means why we waste to grow these metals using ALD? Better to grow metals using some evaporator system or sputting system. So that's reason mostly useful for the oxides. Another the process, that is the plasma enhanced ALD. So again, this plasma is the one of the uh, process in which of course we have this energetic particles with the, we can have this, we can lower the temperature. So it means even in the plasma enhanced ALD, even we can grow means film at the even at the room temperature. So that is the one of the advantage to having this plasma enhanced ALD system. So this is the one of the example like we have taken. This is the, so also in NPL we have the also ALD system to growing this aluminum oxide, hafnium oxide, even this zinc oxide. So as I mentioned, the precursor you have to select a lot of precursor. Like for example, here you are for the aluminum oxide, it is the aluminum metal organic precursor, then dimethyl aluminum butoxide, and then some water vapor, and then some deposition pressure and temperature you have to follow whatever the uh, process. It depends on whether thermal ALD or plasma enhanced ALD. So this is the one of the example like making this ER203. Then here again you have the different precursors. And then after that, people have used this AFM, and from the XRD, they are able to see which temperature or after the growth they have annealed at the different temperature. So this is the one of the process that you can grow the film, and then if you even if you want to change, or if you have the some kind of especially for the oxides and others, even you can anneal at the high temperature, and from that you can from there even you have the control over the quality of the film. So this is again the same thing, just they use some different power, like they use this radio frequency plasma power around 1500 to means 1.5 to 3 kilowatt. So here they are getting the very uniform film. So that is the one of the example, whether you are using the thermal ALD or you have this plasma ALD system. So, as next, I am going to talk about the CVD process. So, of course, when we started the CVD, before CVD, of course, we have recently started the chemical evaluation when this 2D materials comes in the pictures. So, of course, people started this first 2D materials are started, or maybe once the graphene invented in 2004. Then from here, people started to work on the different 2D materials. So it is not graphene. After that, if you see in any lab or any materials, like we are going toward all the materials. First, we started with this compound semiconductors or this kind of like HBN and other things to having the 2D materials. But nowadays, uh, another example is like transition metal dichalcogenides. That is, we have this all the family like MOS2, WS2, MOSC2, WSC2, all other materials. But interestingly, now people, as they found from graphite to graphene, people started to making this monolayer of the each elements. So now the family of the 2D materials is growing day by day. Like people started with this phosphorine. This is the single layer of black phosphorus. Then later on they have started even this monolayer of silicon, that is the silicene. Then germanium, they have got this germanium. Then tin, they have this tininin. Even that is the genes means maxine and all others is coming in the picture. So problem is how we are going to make this single layer or mono layer of this kind of materials for the different application. So of course, one approach is like whatever they use in 2004, this endim Gaim and Novoselov, like using the Scotch tape method, or that is we call this mechanical exfoliation. So what we do, for example, if in case of graphene, we have this highly oriented pyrotic graphite, that is HOPG, and then after that you put the Scotch tape and then you remove one layer. If you are lucky, you can get this one layer. But the problem is you don't have the control over the size and shape, because sometimes if you can get maybe 1 micrometer by 1 micrometer, sometimes you can get 5 micrometer by 5 micrometer. But if you want to make some devices, you have something in the mind that I want 5 micrometer or 10 micrometer. So that's the reason mechanical exfoliation, of course, for the basic purpose we can use, but for the device and other application, definitely you have to go for the reliable technique. So of course people use the liquid exfoliation, but again, as I mentioned, liquid exfoliation or liquid process is mostly this have the more kind of the chemical compounds and contamination. So that is the reason it is not appreciable to have this liquid exfoliation. So now, of course, we can't avoid or we can't do any good research without involvement of chemistry or chemistry means our chemistry people and faculty. So this is the one of the technique that is we started the chemical vapor deposition. This is it means we have the different precursors like we can use this selenium powder or sulfur powder, and then we have this substrate or whatever we want to grow. Then accordingly we can make the different kind of the chemical process, that is we say this chemical vapor deposition, like we heating at the different temperature, we are blowing the different gases. So it can be uh, atmospheric pressure, or it can be even this uh, low pressure vacuum also. That is called the LPCVD, means low pressure CVD process. And from here you can make the different structures, whether you want one layer by layer, like this is MO and then this is sulfur, then you can make the MOS2. But if you want some different structure, even you can make the vertical, in plane, or super lattices. So so this in chemical vapor deposition process, of course, it depends what kind of the carrier gases you have, because sometimes this carrier gas will not only help to flow, means carry this your materials from one place to another place, but also it helps to clean or to etching or to removing on the top of the surface. For example, if you have the mixture of argon and hydrogen, then it means you are even cleaning some of the substrate or even making some nucleation side. So that's the reason we have to select what kind of the gases we are going to flow, and then accordingly how many zones. Basically people say you have the single zone CVDs, two zone CVD, three zone CVD. So it depends what is the application. For example, here I am talking the two zone CVD, but like you have the precursor and then you have the substrate. But in some places you have the three zone CVD, because you have the two different precursor and then you want the two different heating zones. It is not necessary that you can heat only one material. So that's the reason if one material is having the 400 degrees Celsius, another material you can make 600, then you can't use the same zone. So that's the reason you make the two different zone for the two different heating, and then it depends what is the growth temperature, and accordingly you can heat the substrate also. So this is the reason mostly or ideally people have the three zone CVD. So as I already mentioned, here we have this mass transport, like we have the gases, then reactant gases, then again whatever this gas diffusion happening, then it comes from the byproducts. So making again the whatever the thin film process, then finally you are getting some kind of the whatever your requirement. Then accordingly you can making this. For example, in the case of MOS2, generally people use MOO3 and sulfur. So sulfur will react with the MOO3 and then O3 will go outside, means in the form of oxygen or sulfur oxide. So that is called the byproducts. So this, of course, CVD have the advantages, like you can make the very large area devices, and also it is a repeatable process, because once you have know what is the temperature, what is the growth zone, and what is the material you use, accordingly you can change. But the limitation is, of course, again this CBD of the byproducts. So you should know what is the byproducts, then of course you can make this and, neutralize them, because we can't make the our environment hazardous during the this all the CBD process. So this is the some of the example people have used this gallium dope zinc oxide thin via CVD. You can clearly see from here. Then people use this MOH2 thin films, and some of the SNS even they can dope, like they have the precursor C4H9SNS3 and then this kind of precursor and methanol. And from here even they are able to see this MO doped SNO2 thin films by the CVD. So this is the all the procedure. People know that means if you have the expertise in both chemistry and physics, then and if you have the low budget, even you can go for the CVD process and you can do wonder of the works in case of 2D materials and even oxide and other selenide and sulfide materials. So this is the one of the like SNSCT seeds, and they can make using the even singles this zone CVD, like they have this SNSC powder, and then after that they have grown and then get this very high quality SNSC even on the mica sheet. So as I mentioned, even the CVD process have been used for the epitaxial gallium nitride. Of course, they have this kind of the chemical like CH3 and then ammonia gases, and then they heat in presence of the hydrogen. So this is the reason you can use this different gases, and then they form this gallium nitride, and then of course this some 3CH4, and this is the some of the precursor for the aluminum. For example, you have the trimethyl aluminum for the gallium trimethyl TMGA. So this kind of the indium, gallium, and aluminum you can make, and from here you can also grow the gallium nitride film for the high quality of the film. But of course, growth rate is very high. This is 2 micrometer to more than 2 micrometer. That means you are not able to control the single layer like whatever you controlling in the MBE process, but sometimes also you require very thicker film for the different purpose. Then this CVD process is as good as. So MOVP is basically almost similar to the whatever we have this CVD process, and that's the reason this we call this metal organic vapor phase epitaxy, and also it is terms as a metal organic chemical vapor diffusion. So it is the same like CVD technique, which can be used to growing high purity single crystalline thin films of the different materials and different substrates. So here again you have this like gas cabinet, and then after that you have this liquid precursor or gas precursor, and then accordingly you have the different lines you make, like this is the gas precursor, this is liquid precursor, and then after that you have the again the this heating lamps or heating quartz reactor, and from here you can making the different film. So this is the same as CBD, but only you have this option like it is more controlled way, and then you have this different channels for the liquid and gases as well. So this is the more controlled way, and this is mostly for the industry purpose when people have this large area this thin film deposition. They use this MOVP, but for lab purpose mostly we use this CBD process. So, for example, in MOCVD or MOBP process, we have this ultra pure precursor gases are injected into reactors, usually with the non-reactive carrier gases. And then step two, as the precursor approaches the semiconductor vapor, they undergo pyrolysis and the subspecies absorb onto the semiconductor vapor surfaces. And third step is the surface reaction of precursor subspecies resulted in the incorporation of elements into the new epitaxial layer of the semiconductor crystal lattice. So it depends on the what is the application. For example, in case of indium phosphide can be growth with this trimethyl indium and phosphine precursors. So this is the it depends what is the precursor, then accordingly we can choose the different materials. So this is the people use this gallium oxide thin film using the MOBP, and they are getting the single crystalline, highly crystalline gallium oxide film for the different purposes. And then they use even this doping of the aluminum on the gallium oxide using this MOBP. And then some of the aluminum nitride thin film, as I mentioned, we can use this aluminum nitride using this trimethyl aluminum and then ammonia as a precursor. And then we even able to get this high quality like very low racking curve, so it's showing the high quality of the film. So yeah. So if time permit, I will just take 5 to 10 minutes to have just my uh, favorite topic, that is the surface characterization techniques. Manojji, we have time
Yes,
for
sir,
5.
yes, sir. That will be nice actually to
Okay.
at least have an idea how we can see such highly oriented and thin films.
Yeah.
Hmm.
Okay. Thank you. So I'm just going this surface characterization technique. You just see what is the name here. We put this scanning for microscopy technique basically. So I'm just going to focus scanning for microscopy, especially this scanning tunneling microscopy. Because during my presentation, I have shown a lot of the atomic force microscopy images for the different purposes. So why just I will come to this one. So here I just going to talk 5 to 10 minutes on this STM. So this is the two images for the surface morphology we have taken from the SCM, that is scanning electron microscope. So we can see like we have this hexagonal or triangular, this 2D means MOS2. Here we have the worm type morphology of the thin films. But from the SCM images, we are not, means of course we do the cross sectional and then it is complicated. But if you want to see what is the height of this 2D island, or means this 2D layer on the silicon, we are not able to get from the SCM. Same thing if we have this worm type of structure, but we don't know what is the surface roughness. It is 100 nanometer, 2 nanometer, and that one. And then third is like whether we can do atomic scale imaging. Of course, it is not possible because the SCM have the resolution of maybe 1 nanometer or 0.5 nanometer. So that's reason we have to move toward this scanning for microscopy, because the scanning for microscopy we have the all the three directional scanning. SCM have the two directional X and Y, but scanning for microscopy we can move X, Y, and Z. So as already this we are end of the maybe next week it is going to conclude this quantum materials talk. So of course one of the technique that is really made on the quantum base, that is STM. So this is the one of the famous cartoon that when this line is here and then you have the impenetrable barrier and then man is standing here. So it means you have the wall and then line is here, then you are safe in your house because you are considering object as a classical particle, defined mass and energy. But what happen if we consider it is the quantum particles, the line? So it means we have the tunnel effect. Then of course there is no way that man will be standing here, but he has to run away. So on the same principle, scanning tunneling microscopy has been invented. And here we have this STM tip. This is the metal tip and this is the sample. So of course, only limitation is STM that we can do mostly semiconductors and the metals. Of course, insulator it is not possible because we have to have this some kind of the tunneling current. So if we see this is the simple design, you have the STM tip, but here you have this kind of the control voltage or piezo. This is the connected with the piezo voltage. So you have the loop means devices here. Then from here you can control the sample and tip distance, and accordingly you can select which way you are going to have this scanning tunneling microscopy scanning. So here we have these two different mode. Like every system have the different modes to work. So one is the constant height mode. So what happens is in constant height mode you have this substrate and then you have the tip. So tip and this substrate have the all the way the constant height. So it means for constant height, your substrate or your film should be very smooth, because if you have suddenly it like this one, then your tip is because there is not moving, means moving at the same height, it means it is going to damage your tip. Another approach, and 99% people use that, that mode is the constant current mode. What happened here? Just tricky. Of course, it will make the height the same difference, but it follow the trajectory. It means like once you have the tip, you know the surface is smooth, then your tip will be here. But once you know the surface is rough, then your tip will making the going to up using this loop feedback system. And from here, always you have this same current, because this current of this turning current is depend on the what is the spacing or what is the tip height distance. So that's reason it is called the constant current mode. So it is the safe, and mostly 99% we use this constant current mode for the STM. So this is the example. Like again, as I mentioned, every UHV system have the two chambers. One is this like preparation or load lock chamber, another is main chamber like growth, and then some of the chamber have the STM stage. So this is the one of the system I worked during my PhD. That we have this load lock preparation chamber. Then after that we have the load lock here, and then after that we move the sample here. Even we can have this AES lead monitor, and this is the STM stage. And then this pressure is always in the range of 2 to minus 10 millibar. So it means we have the always USB system. So this is just working principle, just simple. Like we have this tip is we know this is metallic tip, like whether it is tungsten or platinum iridium, and then we have this different samples. Like for example, if you considering the semiconductors, then once we are applying the sample bias positive, then it we say this empty state, because current is flowing from the tip to the electron flowing from tip to the some sample, and vice versa. Once we have this field state, means if we have the negative bias voltage to the sample, then it means it is this electron flowing from the sample to the tip. So really it matters. Yes, it really matters in the case of the STM. So for example, here we can see this is the well-known silicon 1 7x7 structure. So this is the one of the people have started in this modeling, like they can have this 7x7 reconstruction. So they have this dimer datum stacking fault, that is DS model. So again, as I mentioned, in the UHB, you are able to see, or even for the whether your STM is working properly or not. 99% people use this silicon 1 7x7 reconstruction. It is again the same story. Like in the UHV system, you have to heat 850 degrees Celsius for 30 to 35 minutes to remove the silicon oxide, and after that you have to suddenly heat up to 1000 to 1100 degrees Celsius for 10 to 30 seconds, and then you cool down to the 850, and then cool down to room temperature. That's the reason you are able to see this reconstruction is forming on the top of the silicon 111 cell. And again, if you have this scanning in the empty state, you can see the same morphology, having the very nice hexagonal structures surrounded. But once you have this field stitched image, you can see this medial wall is going to the down, and then this have the this hexagonal pattern or the tetragonal structures. So as I mentioned, of course, you can use NAT, means in the locally you can grow the film, or even if you want to know what is the crystal structures, or even at the nano scale, you can use the STM. So for example, here we use this HOPG substrate, like very high quality, means you have this large terrace sizes, and from here you can grow. For example, we grow this different nanostructures, like we grow like 3D structures, 2D structures, 1D structures, and after that we also control about the 3D islands. So for example, we are able to grow only 3D antimony islands. Then after that you scan all the area, large area, then you move to the 50 nanometer square area. You can see here on the top of this one in the flat surface. Even after zooming, you can scan at the 10 nanometer or 8 nanometer area, and from here you can see crystalline structure. So it means even in the locally, from the STM, you can measure what is the step height. Also, you can measure what is the crystallite structures. And from here, also you can correlate whether it is following your substrate and your grown film or not. And even if not, then whether it is epitaxially or it is the local epitaxial, or even it is the crystal structure at the nanoscale. So, for example, we have made this 3D islands. Then also we have grown these 2D structures like layer by layer. Again, from here, see, we have this step height. We just draw the line, and from the drawing the line, we are able to see what is the height. So here we are able to see, okay, this is the height. So height is around 4.3 angstrom. So it means we are sure that, okay, this is the similar as the antimony 111 structures. Like we have this XYZ, and then from the top of this one here we are able to see lateral period is 4.1 angstrom. It is the showing the formation of antimony 111 phase. So same thing like we can do for the different structure from it looks like 3D 2D 1D, but once we are going for the 1D nanorods, we are able to see it is not the antimony 111 structure, but it is showing the antimony 110 structures. This is the even from the same material we have the different structures, and then different structures have the different nano or different crystalline structure. That is, we can only do from the in situ, or at least because we are not exposing, we are growing the film, and from the same chamber we are after growth we moving the STM stage without breaking the vacuum. Always vacuum is 10 minus 10 millibar. Then we are able to scan, and then we can clearly see this kind of the crystalline structures. Like for example, even we are able to see like only there is no growth here. Just locally we can see like this is the 200 nanometer stadium size of the structure, and then from the top of this one we are able to see this is again showing the bismuth 111 structures. Like here we grow some of the nano rods or nano platelet structure, and after zooming again we are able to see this is the bismuth 110 structure. Even inside that this one we are able to see exactly whatever the crystal light is the form for that bismuth 110 structure. So this is the some of the example. So I just summarized that I briefly discussed the importance and basic of various nanostructures, nanomaterials, and especially epitaxial thin film for the quantum and other device application. And in the first part, I discussed the MBE, PLD, laser MBE, and read etc. And also I try to show some of the real videos how we are going to monitor or how we are going to do this all the procedure inside the vacuum system, and also read analysis. And then second, I try to cover ALD, CVD, and MOVPE process, and mostly this UHB STM to see the atoms at the nanoscale. So just take away message is this growth of epitaxial thin films. We have the various application. You name anything from quantum device to energy devices to LED, solar cell, magnetic devices. Anything you are able to see. Mostly people try to grow the epitaxial thin film. Of course, it depends on the what is the application. Accordingly, they have selected the different growth techniques. So I would like to thank my collaborators, mostly myself and Dr. Senthil work on this laser MB system, and some collaborators from the IIT Madras, SSPL, and BITS Pilani. And I would like to thank my director, Professor Benugopal Achanta, for his kind support, and also even we are moving toward this quantum materials for the metrology application. So in future also we have this nanofabrication facilities at NPL. Already this massless lithography and the etching system we have, and then we are getting this electron beam lithography in the end of this year. So most probably we are able to make these quantum devices. So I would just thank for the CSIR and other funding agency for our work. Yeah, so I thank you for your kind attention. I just taken 10 minutes extra because I was some confusion with my laptop on this one. So I hope I finish on time. Yeah.
Yes, sir, very well on time, and this is fine. Actually, you covered more or less all the relevant techniques for thin film growth. And you also showed us the instrument part, live videos, and I mean recorded videos, but the growing part and the instrument part. And it was really nice that you proactively contributed to the characterization techniques, because when we talk about such high quality thin films, it really require high quality characterization techniques also. Otherwise, such patterns or such atomic ordering may not be visible in normal techniques. So, sir, there are some queries from participant side from Dosia Parveen. Why is epitaxy important in semiconductor devices?
Yeah, so epitaxy is important because when we have this, for example, just taking the simple example, if we have the silicon substrate, but even on the silicon substrate, even if we grow the silicon epitaxial layer on the silicon, then we have the control over the doping. For example, you can select only silicon substrate, either P type or N type. But if you after that, if you want to make again P type, you can't make the two substrate connecting each other. So it means you have to grow the epitaxial film, then you have the doping. And again, if you the third layer, if you want the different doping or highly doped or undoped, then you can make the you have the selections. So that's an epitaxial thin film have the more advantage. And most of the devices you want this kind of the epitaxial film.
Yeah, okay, sir. So, I also want to request you to elaborate on this uh, state of the art in India related to the technology development, or we can say mm, thin films for quantum technologies specifically.
Yeah, so for the quantum technology, now the recent materials topological insulator materials. So people started this making the topological insulator the single crystals. But as I mentioned, because single crystals have the limitations, because you can't make P type, N type even in the one single crystal. So that's the reason you want to grow the epitaxial thin films. And this topological insulator, people use this magnetic doping or some other dopings. Then from there, they are going to make this anomalous quantum Hall effect. That is the one of the uh, field, and of course that you can do this make different spin based devices. So this is the one of the and already from the quantum materials, I think some group they got some funding for the MBE to making this kind of the this 2D materials plus topological insulator for the this quantum devices.
Yes, sir. It is actually a common question. It was raised by Dr. Lakshmi Narasimha Rao in previous talk also, that some general information regarding the infrastructure available in India for development of different quantum materials. How about the scenario across the globe? Can India take lead in quantum materials instead of importing those materials for technology development?
Yeah, I think this, especially for the quantum materials, like quantum materials hub is in, I think, at IIT Delhi. Professor Rajendra Singh is looking toward this one. And then this making this quantum materials, already some funds has been given for growth of these 2D materials. And others using this MBE system. So definitely we are going to be more independent in the near futures. I have just a simple example recently, because we are working on the gallium nitride, and some of the work also we wanted to import some of the gallium nitride wafers, but due to the war and due to this, people know this gallium, especially gallium nitride, or the high application radar and missile systems, that even this company from the overseas, they are refused to give, because they say we are not protecting. So that's the reason we have to be self-reliant to get these quantum materials. And then, of course, this government is working toward this one. So hopefully, of course, as a researcher, we know it will take some time, but definitely we will achieve something. At least we have to make the self-reliant. For example, when people start with the graphene, we are not able to get the graphene. But if you see nowadays, even in the university level, even college level, people are able to grow this graphene. So that is the one of the uh, beauty of having this all the infrastructures and experience. Even like during the talk and our discussion, we can have these ideas, and then we can go back to our lab or institute, and then we can think about this. Yeah.
Yeah, so I think slowly we are focusing on our own self-reliance
Yeah.
in semiconductor devices, quantum devices, materials, every field sector, I would say. So now slowly we will develop these things. And yeah, I think uh, this may be similar. Like what in the previous lecture we have heard that thin films growth or crystal growth or these material development techniques, they are not for the kind of lectures, they are for the practical learning. So once we do it, we learn, and it takes a lot of time, energy, efforts, understanding to optimize the growth for such high quality material. So although we see a very nice image, but to make that very nice material, maybe it's months or years, maybe. You can also elaborate on this part, because otherwise it is mistaken that that any material we can grow right away in very high quality.
Yeah. So so as I mentioned, starting, like I have shown one of the graph, that is the temperature versus flux. This is just one of the example. That first you have to select the materials, and then what is the substrate you want to use. After that, you have to also know what is the temperature, or which temperature range you are getting the high quality, and then again you have to control the what is the deposition rate. So this optimization, sometimes, of course, you have to go through the literature as well, and then it takes at least few months. And most unfortunate thing is that if your system break down, or if you, because see, we are talking the ultra high vacuum system, this is just simply we are saying, oh, you have the UHB and 2 to minus 10 millibar. But you just see, we have the, for this achieving this one, you have the three pumps. One is this dry vacuum pump or dry roughing pump, that is we can go from atmospheric to -3. Then after that we have the turbomolecular pump, that is we are reaching to -8 to -9. And then from the maintaining -10, we have this ion pump. And then ion pump is also supported with this titanium sublimation pump. So we, it means we have the four pumps. Then we have the accurate ion gauge reading, that there is two different gauges. One is the vacuum gauge for the normal, like Pirani gauge, and for this full range we have this up to ion gauge. So that's reason, even to maintaining the vacuum and measuring, we have the 6 to 7 equipments. So if something go wrong with some any equipment, you are not able to see the pressure -10, or you are not able to achieve the pressure -10, because you have even dry scroll pump, even it is just giving 10 over -3. But the problem is, like, these pumps, like turbo pumps and ion pumps, only they can work after 10 to -3. They will not start from the atmospheric. So it means even this dry scroll pump, that is the range from atmospheric to -3, it has the huge means these pumps have the huge dependency on the dry cold pump. So this is the like one of the challenge. Another challenge is, of course, when you are cleaning the substrates and you are making the substrate, and of course, as previous audience asked, dependency. So sometimes, if you are lucky, one batch you are getting very high quality of the substrate, but sometimes if you are, because you don't know, because who is the supplier and what he is supplying. So that's the reason it is very necessary, and we are timely now started this semiconductor manufacturing unit also here in India. So hopefully at least we have the control over to getting the high quality of the single crystalline wafer as well. So that is the one of the advantage, and most importantly the high purity materials. Like when you are growing MBE, we can't use 99%. We have to get the 99.9999, at least 69 pure materials. Like gallium should be 69, gold, platinum, whatever, even Mali, all the materials should be 69 pure. So it means you have this 99.999999. Okay, so this kind of the things, of course, it is a challenge, and of course, it required a lot of the money as well, because it's the costing. Because you just simply you have this argon gas 99.99, maybe you can get 2000 rupees, but if you say 99.999, you get 5000. But if you say 969, then it will charging around 40 to 50,000. So this is just one nine is so much critical. That is the that is the one of the, so a lot of challenges. And then of course challenges also make us to learn how to repair our system, how to have the knowledge about the vacuum, how we are going to make the materials. So this is the one of the way. It is not that your system is always running 24/7 all the world, then it will, you are not learning anything. If something wrong, then you are able to see. Otherwise you just press the button, okay, go here and then do the deposition, finish. Then it is not the case. Means definitely everybody system breakdown, whether it is in USA, Germany, Singapore, or India. But uh, problem is, this is the way that we are learning, and we have the ideas, and again we are still learning, like from one system to another system. Yeah.
Yeah, exactly, sir. You highlighted a very important aspect. Uh, the money involved in making such high quality material is also very demanding. Maintaining such systems not only requires money and time, but also you need to learn from each of your mistake, and you need to take care of each and every small part of the machine. Then only you can work out. And there are actually the requirement of ultra high vacuum and other stuff requires ultimate care for the machine. So many things are there, and this may be the reason. I think only selected labs they can produce such high quality thin films. Maybe you know better. All over India, if we count how many such labs may be there.
Yeah, because it is very few labs, and that's reason this quantum have the, so one of the advantage, that if you have everybody do not need to make the materials, but you can contribute making the devices, or making some characterization, or making some other application, and then you can uh, give your recipe to the whoever the grower of these thin films, and then they will help you to grow such kind of the film, and then you can use that material for the other devices as well. So this is the, I think, a good idea, because everybody have, for example, if 100 MBE systems, and then everybody growing the same thing, but if that will be huge loss. It is better to have some other expertise, and then we can jointly work, and then somebody can grow the film, then somebody can make the devices, because after that making devices is also one of the challenge. It is not so easy. So that is the way, yeah, to move ahead.
Okay, sir. So we have taken a lot of time from you already. So I would like to thank you so much. It was
Yeah.
really nice, actually. You godly accepted, heartfully accepted our invitation for the lecture, and it was really nice lecture. Many new things I personally learned from your lecture talks, and hopefully some participants they may also get motivated to for such type of work, and they may contact you directly. So we normally provide them the lecture slides what you used for their reference, because not all members they are online during the lecture. Some members they follow the video lecture later on. So once again, sir, thank you so much.
Yeah.
And
Thank you.
yeah, and for the participants, tomorrow is Sunday. There is no class on Sunday. We'll meet on Monday. So with this, thank you very much, everyone. Thank you, sir.
Yeah.
And hopefully we'll meet offline also soon.
Yeah.
I'll,
Sure.
yeah.
Sure. Sure. Yeah. Yeah.
Okay, sir.
Okay. Yeah.
Thank
Thank
you.
you.
Bye.
Okay. Bye.